Hello everybody. We want a simple method to evaluate integrals without having to fall back to Riemann sums. We can use integrals to define functions. We will call these newly defined functions area functions. You start with a continuous function. Remember, for us, continuous just means no jumps. And you fix a number a as the left endpoint of your interval of integration. The right endpoint x is variable. Then the area below the function defines the area function capital A of x. If you move x to the left and to the right and watch the area becoming smaller and bigger in your mind's eye, you may think of the curtain of the theater which is opened and closed. Note that the variable x is the upper limit of the integral. So we need to use a dummy variable inside the integral. Anything but x will do. Here they chose t. This picture shows the graphs of the original function here and its area function and how they are related. If x equals b, the first picture, then there is some positive area and we get this point here on the graph of a of x. If you move b back until it meets a, you open the curtain in the theater completely, then there's no more area left and you get this point on the x-axis. If you close the curtain until c, which is a 0 of the original function, then the area function will reach a maximum. Why maximum? If you go even more to the right, for instance till d, then you subtract the part of the area below the x-axis and the graph of the area function will decrease. Here you see again the official definition of the area function. As a first example, we have a function f, which is only given by a sketch of its graph, plus we happen to know the absolute values of these three areas here, so it's 27, 3, and 35. There are two area functions. A of x has a lower limit minus 1, and we have to determine a of 3, a of 5, and a of 9. A of 3 is the integral from minus 1 to 3, which is minus 27. Remember, everything below the x-axis counts as negative. A of 5 is minus 27 plus 3, and a of 9 is minus 27 plus 3 minus 35 is minus 59. The second area function is called capital F, and it has a lower limit x equals 3. Again, we are asked to find f of 3, f of 5, and f of 9. Here we have f of 3 is 0. There's no area between 0 and 0, between 3 and 3. f of 5 is 3 and f of 9 is minus 32, 3 minus 35. There is an interesting question which is not in the book. What would be f of minus 1, capital F of minus 1? If you replace x by minus 1, you get a case where the upper limit is smaller than the lower one, so we have to flip and negate. So f of minus 1 is minus the integral from minus 1 to 3, so minus 27, which is plus 27. Please note these hints to related exercises. It is a good idea to study such a topic, but really helpful method of learn a little, do a little. So stop reading here and do the exercise 12, which I assigned right now, then go on reading or listening. In the second example, we have a linear function as f of x. Here we can use the trapezoid formula to actually compute the area function a of x. Lower limit is 2. In a, they want a of 2, which is 0. In B, you have to compute a of 5. Well, you plug 5 and 2 into the area formula. In C, you have to replace 5 by a general x, which gives this quadratic function. Here's a graph of the area function. This picture shows all the elements, and here's the final result. In D, you are asked to compute the derivative of capital A of x. And if you do this, then it turns out to be exactly the function f we started with. And this is not an accident, but the first part of the fundamental theorem of calculus. So we want to show that always capital A prime of x is f of x. Or in other words, we want to show that the area function is an antiderivative of f. Let's start with recalling the definition of a derivative. For the derivative of f at x, we had to compute a slope of a secant through x, which would be this. And for smaller and smaller h, this term converges to the derivative. If we replace f by a, we need to study this term here. Luckily, we can do this by means of pictures. We start with the difference in the numerator. They choose a rather large h here, otherwise there wouldn't be much to see. The difference between a of x plus h minus a of x is this shaded part here. If h is very small, then this area is approximately a rectangle. And its area then is width times height, so h times f of x. So we get this almost equality, which we can divide by h and go to the limit. And here we are. Capital A prime of x is f of x. So here the limit is easy because there's no h, so this is just a constant. This is not a formal proof, but it should convince you. If you want, you can read the formal proof for yourself at the end of the section. It's the same idea, but without this wobbly equality sign. Here is the official version of the first part of the fundamental theorem. The upshot is that the area function is an antiderivative. How can we use this fact? Remember from the video before that antiderivatives only differ by a constant. So if you have any antiderivative f, then this will be the area function plus a constant c. If you take the difference and replace both f of b and f of a, then c cancels and a of a is 0. So only a of b survives. But a of b is a definite integral with lower limit a and upper limit b. So here's the second part of the fundamental theorem. In practice, you will use a shorthand notation for this difference, and you should check that you get 1/6 if you evaluate this term here. On a higher level, the relation between differentiation and integration is the same as the one between, say, square roots and squaring, or taking powers and taking logarithm. The one undoes the other. These are all inverse processes. If you first integrate and then differentiate, you get back to the function you started with. This is the first part of the fundamental theorem. And you can flip both operators. If you first differentiate and then integrate, you get back to f of x as well. This is the second part of this fundamental theorem. Just replace b by x here and use a dummy variable inside the integral, and you will get it. Let's do something with this theorem and evaluate some integrals. Sadly, we will right now only be able to do the first example. You will see why in a minute. So we want to evaluate this integral. If we look at the graph, we want to compute the area under the parabola between 0 and 10. It's easy, we just need to find an antiderivative. Remember, any antiderivative will do. So then we plug in 10 and 0, and the result is 1000. We can't do the second example because we don't know yet about the derivative of sine and cosine. This will be the first thing we do in August next semester. C doesn't look good at first sight, complicated function, but then we see that we can simplify the function and write it as a sum of powers, t to the minus 1/2 and t to the minus 1, but unfortunately the second term is t to the minus 1, and as I said in the last video, the antiderivative is the natural logarithm, which we didn't deal with yet, so we will abandon this example as well. But remember this trick of simplifying a term. In other cases, in the exercises, this will work. It is a really good idea to stick to learn a little, do a little, and do right now the exercises in the range of 41 to 50, which I've assigned on Teams, at least a few of them. Example 4 is very similar. In A, you need to compute the net area. For this, you integrate from -1 to 2. In B, you need to compute the area, or total area as I will call it. For this, you need to evaluate two integrals, one from -1 to 0, and the second from 0 to 2. In example 5, you use the first part of the fundamental theorem. So in A, just remember that d dx and the integral cancel each other. In B, you see that you first have to switch top and bottom, which gives you a minus sign, and these two cancel, and so this will be the result. In C, well, we can't do this because it involves a chain rule, which we didn't learn yet. Example 6, this is a conceptual example, no calculations, just sketching. So a function is given by its sketch, and you only know that these four regions all have the same area. You're asked to find the zeros, the maxima and minima, and then to use this information to sketch the graph of the area function. As before, the area will increase till x equals 4, then it will decrease until 8. So you have 0 at 0, the maximum at 4, 0 at 8, and then it starts again, becomes periodic. Again, well, here we have the proof of the fundamental theorem, but we will skip this. And again, start with these 10 review questions and then finish the exercises which you have not done yet. Thank you for watching.